Hello there. Want to welcome you to AI for Humanity, a group of wonderful thinkers who will talk about the chance of a lifetime for AI and humanity. To start us off, I'd like you to meet the Chief Scientist of AFOSR, Dr. Roach. We call him Pat Roach. Take it away, Pat.
Well, thank you very much, Doug, for the great introduction, and it's really a thrill here to be here for your panel, which we'll talk about in just a second. But I want to remind everyone that the Chief Scientist Distinguished Lecture Series tries to bring in the brightest and best around the world from academia, government, and industry to talk about critical problems going forward, and to talk about science and how to get at that science and how that makes a difference as we go forward. So our Distinguished Lecture Series involves our program officers and international program officers who seek out these folks to bring to us information on currency and the like. And so it couldn't be more current today. I'd like to again thank Doug for putting together the AI 2040 and Beyond panel that hails from industry, academia, and government. And Doug will be doing a lot more introduction than I will on that. But I want to say that this couldn't be more timely. Just yesterday, the President of the United States signed an executive order essentially on the safe, secure, and trustworthy development and use of artificial intelligence. One of Doug's invitees, Professor Yann LeCun, will not be with us live, will be with us virtually, but he is on his way right now to the UK to be part of the Prime Minister of the UK's announcement on their implementation of artificial intelligence and safety. And so without further ado, please welcome back Dr. Doug Riecken.
Hi there. First, I want to thank Pat. Pat, it was wonderful. Now, we're going to go forward, but I have a little game here. If anybody could guess who these two people are over my shoulder here in the corner of the garage, send me an email. You might recognize the guitar player or the wonderful piano player. I want to now give a quick shout out for Gloria Rudish-Mensky and her husband, Marvin Mensky. Now going on, Mark Maybury and I have known each other for at least 25 years, different boards with the ACM and whatever. And he has a really, really good video I want to play for everybody that really highlights many different ways AI is impacting humanity worldwide. So let's go see what this video will show us.
AI ML is becoming a huge thing, especially in the research field, but machine learning itself is really hard for people to understand. Even the people who design them can't necessarily explain them to you.
It's kind of defined as the ability of machines to perform tasks that require human intelligence.
And the AI model is supposed to be a representation for something in the real world, like a problem or like a way to solve a problem.
In terms of even understanding what AI is, a system that's designed to actually make decisions that were typically left to human intelligence.
You log into Netflix and Hulu. How does it automatically know I should be watching this TV show or this movie next, right? That recommendation engine built on AI.
AI ML is really cool, and there's a ton of different applications we could use it for.
AI doesn't have to be complex because it can be really simple and still create remarkable improvements in our lives.
What should we learn to get ready for this new world? How will these new tools impact how we live?
To understand where we are, let's look at where we began. In less than a century, humanity mastered the depths of the oceans, soared into the air, and extended our reach to space. Artificial intelligence, it applies to everything, from art to music to movement. If you think about artificial intelligence not as being a machine-based intelligence, but rather as augmenting the intelligence of the human, it now becomes a much more powerful tool The true value is not in replacing humans, it's in augmenting intelligence to enable us to be better selves. I'm Dr. Mark Maybury, the 33rd Chief Scientist of the United States Air Force.
Wonderful. Well, now we're going to hear the way to say bonjour the proper way from my dear friend for, at least almost 30 years. I've known him through so many different kinds of science and music. So I turn the stage over to Yann LeCun. Take it away, Yann.
Hi everyone, my name is Yann LeCun, and I'm really sorry I can't be with you today. I'm actually on a plane flying to the UK for the AI Safety Summit organized by UK Prime Minister Rishi Sunak. I want to tell you about a number of different topics today, but the title is Objective-Driven AI. This is not going to be a technical talk. And the idea of objective-driven AI is basically a new proposal for a new type of architecture to build AI systems based on a kind of cognitive architecture, an old concept, of course, in AI. And the idea is that AI systems should be driven by objectives. In other words, the output they produce should be the result of optimizing an objective and using a model of the world to figure out, for the machine to figure out whether a sequence of action that it can imagine will optimize an objective, satisfy a number of guardrails. And the idea behind this is to allow machines to plan, reason, and also be controllable, because if we can set objectives to them, they can't deviate from them, then that makes them controllable. That also makes them safe. Behind this is the question of how do we get machines to learn as efficiently as humans and animals. We've made enormous amounts of progress in AI in recent years, but we have systems that can pass the bar exam. We have systems that are very fluent, can manipulate language, multiple languages simultaneously, as a matter of fact, can retrieve a large number of facts, at least approximately. They seem to be able to reason, but not really. They are mostly able to retrieve forms of reasoning that were previously exposed to during training. And there's a lot of interesting studies about this. But the question is, how is it that any 17-year-old can learn to drive a car in 20 hours of practice, and we still don't really have full autonomous level 5 autonomous driving? And the systems that we have that can approach this require enormous amounts of engineering and mapping and all kinds of sensors that make the system more secure. So we're not approaching human level intelligence, and we're not approaching the capabilities of humans to learn new things. And driving may be something that's rather complicated, but what about, I don't know, cleaning the dinner table and filling up the dishwasher? Any 10-year-old can learn this in one shot, in a few minutes. And we still don't have robots, domestic robots, whose capability are anywhere close to this. And it's not because we can't build the robots, it's because we can't train those systems to do those things. In fact, we really don't know how to train robots or AI systems to learn how the world works, the same way little children and baby animals learn how the world works by essentially watching the world go by. So this is kind of curious, because we do have systems that can do this from text. So using self-supervised learning, which basically consists in learning to fill in the blanks, we can train text understanding systems. And the procedure is extremely simple. As many of you know, you take a piece of text, You remove 10 to 20% of the words that are in it. You put this text at the input of a gigantic neural net, a transformer architecture, and then you train the neural net to predict the words that are missing. Depending on the precise architecture of this neural net, you can then use this neural net to just encode text, and you can train it in multiple languages, and it will encode the text in representations that are to some extent language independent, which is astonishing. And then you can use the internal representation learned by that system as input to a subsequent task, like translation, summarization, or things of that type. With a particular architecture where the attention inside the network is causal, you can train those systems to just predict the next word in a text and then fine-tune them to answer questions, right? This is autoregressive large language models that many of us have become familiar with over the last year. Those systems are, on the surface, really impressive, but they really do not understand how the world works because they are trained purely from text. They don't understand basic principles, for example, that if A is the same as B, then B is the same as A. They don't understand that if A is larger than B and B is larger than C, then A is larger than C. So despite the enormous amount of data that those systems are trained on, there are very basic concepts that they just do not capture. And it's probably because they don't have any experience of the real world and the physical world. And this is what animals and humans are really good at. Now, a lot of people have had the idea of training systems from video using the same kind of technique. So you take a piece of video and you remove pieces of it, maybe the latter part of it, or maybe some frames in the middle. And then you train a gigantic neural net to reconstruct the parts that are missing. And sadly, this doesn't work. You don't get any good representations of images or video if you do this. They don't really perform very well. There's been a number of projects on this, actually going back a very long time. But most recent one being something called Video MAE, which means masked autoencoder. So this is very similar to the kind of systems that are used in text, but it really doesn't work very well. And we can ask ourselves why. What is so different between text and images and video? The difference is that text is discrete. And so if we need to represent an uncertainty in the prediction, it's relatively simple. We produce a large vector of numbers between 0 and 1 that sum to 1 that represent a probability distribution over every token, which are subword units in the dictionary. Typically in a language, there would be 30,000 to 40,000 such tokens. So every prediction is basically a 40,000 dimensional vector with probabilities for every possible word. Now, the bad news is that we don't know how to do this with images or videos. We don't know how to represent proper probability distributions over all possible frames of a video. And this is why those techniques don't work for video. So I've come to the conclusion over the last several years that the best way to handle this problem is through an architecture I call JEPA. That means Joint Embedding Predictive Architecture. And the idea of JEPA is that instead of having a variable X that you observe, let's say a segment of video, and then training a system to predict a variable Y that you observe by weighting, let's say the continuation of that video, using a generative model that will produce Y or predict Y, we are not going to use a generative model. We're going to take X, run it through an encoder, and take Y and also run it through an encoder, and then perform a prediction in this embedding space, this joint embedding space. Hence the name Joint Embedding Predictive Architecture. Now the trick is the big question is how you train those systems all at once, because you could of course pre-train a visual encoder, but that's kind of cheating. And so what you like is a technique for training a system of this type all together. And we now have 2 or 3 methods that work really well for this. One of them is called IJEPA. Another one is called VICREG. That means variance, invariance, covariance regularization. And both techniques basically consist in making sure that the system does not collapse. So basically that the information extracted by the encoders is as informative as possible about the inputs, but at the same time not too informative so as to make the prediction task impossible. Because if you preserve all the details of a video and you try to predict all the details in a video, it's an impossible task. There's all kinds of things that can happen in a video that are completely unpredictable. If I take a camera and I point it at a scene, maybe outside, there's no way I can predict the motion of the leaves in the tree, the ripples in a pond, the motion of the blades of grass and things like that. Those are kind of more or less chaotic. And so what you want is a system that makes prediction in representation space where a lot of those irrelevant details have been eliminated. So that's the idea of a JEPA. Now, from the JEPA to a world model, there is a small step, and that small step is a causal JEPA. So that's a system that observes the state of the world, let's say from vision, imagines an action that an agent might take, and then predicts the next state of the world in representation space. So now what you have is a causal model, state of the world at time t, an action I might take, state of the world at time t plus 1. If you have such a model, which is again, can be implemented by a JEPA and trained and self-supervised by just observing video and observing actions being taken. If you have such a model, you can unroll that model in time and then imagine a sequence of actions and then compute the likely result of taking the sequence of actions. Now what you can do is feed that predicted outcome to an objective function that measures to what extent a task is being accomplished, and with a combination of other terms, perhaps measures to what extent the behavior of the system was safe according to some guardrails and criteria. So now what the system can do is plan, through optimization, plan a sequence of actions that will optimize these objectives. That's objective-driven AI architecture. This optimization can take place in continuous space if, although the modules are differentiable, you can backpropagate gradient through this and figure out by optimization a sequence of actions that will minimize the objective according to the prediction of your world model. If the action space is discrete, you might have to do something more combinatorial in terms of optimization, perhaps a tree search or something of that type. But if we remain in a continuous space, that makes the optimization easier. Okay, we're not done yet because most planning tasks actually require hierarchical planning. If we plan to go from, I don't know, New York to Washington, D.C., we have to, let's say I'm sitting in my office in New York. What I need to do first is go to the station and catch a train. How do I go to the station? So that's a two-step plan, but it's a very high-level plan in an abstract space. How do I go to the station? Well, I need to go down on the street and take the subway or perhaps hail a taxi. How do I go down on the street? I have to get up from my chair, go to the elevator and take the elevator down and walk out. How do I actually go to the elevator? I have to stand up, perhaps grab my bag, open the door, blah, blah, blah. And you can imagine that there is this entire decomposition all the way down to millisecond by millisecond muscle control. That's hierarchical planning. No one knows how to get machines to learn how to do this. We know how to do hierarchical planning by engineering the various levels in the planning and the representations of the action plan at various levels. But what I'm talking about here is how do we learn appropriate hierarchical representations of action plans within our world model so that the system can spontaneously learn to do hierarchical planning. And nobody knows how to do this. I think this is a huge challenge for the next few years in AI. So 3 challenges. First thing is training world models from video. training hierarchical world models from video, where the high levels make long-term predictions with sort of abstract actions, and the lower level makes shorter-term prediction with more precise prediction. The second one is getting machines to reason and plan. And if we have world models and this optimization procedure, which is very classical in optimal control, it's called model predictive control, then we can have systems that can reason and plan. That would be a huge improvement over current AI systems. And then lastly, how do we do this hierarchically? How do we get machines to learn hierarchical world models, hierarchical representations of action plans, so they can do hierarchical planning the way humans do it, but also the way animals do it. Cats certainly are able to plan trajectories in a hierarchical manner, and they're really good at it. And certainly dogs can do it too. So how do we get to that? It might take the better part of the next decade to answer those questions and get systems like this to work. But I think what the result could be is systems that can lead us to animal level AI, perhaps human level AI, within a relatively short time. Thank you very much for your attention.
Hi there, we're back again. I would like to now have you meet a wonderful dear friend and thinker. This is going to be a wonderful story of many different types of AI. And let me turn the stage over now to Carla. Go ahead, Carla.
So that was a great talk, and actually I will touch on some of the topics that Yann mentioned. So let me share my screen. Can you see my screen?
Yes, we can.
Okay. So, well, it's very exciting for me to be here, and I want to thank Doug for bringing us together for this fantastic AI for Humanity event, a fun event, as Doug puts it. And you know, to start, I will tell you a little bit about computational sustainability, a new interdisciplinary field that aims to leverage AI and computational methods for sustainable development. Sustainable development encompasses environmental, economic, and societal needs. And in fact, the ultimate goal of sustainable development is human well-being of current and future generations. These notions, the notion of sustainable development was initially put forward by the United Nations report known as the Brundtland Report, or Our Common Future. But more recently, the United Nations put forward a very ambitious set of 17 goals, known as Sustainable Development Goals, or SDGs, that range from, you know, no poverty, no hunger, health, education, equality, clean water, clean energy, and the protection of our planet with climate action and the protection of all types of life on Earth. Let me give you some concrete examples of computational sustainability research. For example, we are developing AI strategic planning to reduce the adverse impacts of the hydropower expansion that we are witnessing in the Amazon basin. And as we imagine, you know, they are building all these hydropower dams to produce energy. And in fact, often we think of dams or hydropower dams as clean energy, but the reality is they, hydropower dams can also have tremendous negative impacts on ecosystems as they fragment the river, leading to impeding fish migration, navigation. They can also lead to deforestation and flood of areas. And because of that, actually, they can lead to increase of greenhouse gas emissions as they flood huge areas that lead to the composition of organic matter with the release of methane. So, you know, Yann mentioned the importance of thinking in terms of objectives. And in fact, when we design our systems, decision-making systems, it is important to consider not a single objective, that's actually the standard mode, but consider multiple objectives as, you know, typically our actions can have impacts across different dimensions. So we've been working on this project. Another example is AI to combat the rapid decline in biodiversity, which is, you know, with climate change, the reduction of biodiversity is dramatic. So, for example, we are developing very fine-grained models to understand the distributions of species across landscape over time, and strategic planning to protect, to build reserves or wildlife corridors to protect the species. And as a final example, we are developing AI technology to accelerate materials discovery for renewable energy, for example, for solar fuels. I'll talk a little bit about this example. Perhaps a key message that also, you know, is related to Yann's comments is that it is pure data-driven AI and ML are not suitable for scientific discovery and decision-making. Over the last years, we've witnessed incredible progress, AI progress, focusing on data-driven AI and namely supervised deep learning, with incredible successes where we can actually have superhuman performance for face recognition, speech recognition, and ChatGPT, of course. But there are many challenges when it comes to scientific discovery and decision-making. Again, also Yann mentioned that, you know, the majority of the tasks we deal with are mainly unsupervised or very weakly supervised. And we also have, you know, decision-making. And so often we have to deal with large number of combinatorial choices, for example, where to build the hydropower dam or what experiment to perform. And that leads to huge, large search space with the curse of dimensionality. So to tackle these challenges, we really need to combine what I would say data-driven AI with knowledge reasoning and knowledge-driven AI, so that our systems, our AI systems, can reason from first principles, factoring prior knowledge the same way scientists, they don't start from scratch, they have all their prior knowledge. And that allows our systems to do self-supervision and generalize way beyond the training data and dealing with unsupervised settings and combinatorial choices. And as I also emphasize, we need to develop more ethical AI systems for decision-making that can reason across different dimensions and objectives, not a single objective. So to give you an example here is, I will talk about deep reasoning networks, a framework that combines learning and reasoning. And here is you see some symbols and letters, but it's not really, it's not clear what they are. But now if I give you additional prior knowledge and I tell you, well, these symbols and letters come from two overlapping Sudokus, one on digits, another one on letters, and I tell you the Sudoku rules that you cannot repeat a symbol in a digit, row, and column, and block. Now maybe we can make sense of these symbols, but it's still hard. Well, but you know, deep reasoning nets, the framework we developed that combines deep learning with reasoning and reasoning about prior knowledge, and here the prior knowledge is Sudoku rules, can demix these two Sudokus by really reasoning about the Sudoku rules via this interpretable latent space that actually allows the network to capture the digit probabilities and the shape embeddings and reason about the rules of Sudoku. So, but maybe way more importantly, deep reasoning nets can solve crystal structure phase mapping, a very challenging core, long-standing problem in material science that aims to what we want to infer crystal structures from X-ray diffraction patterns. And here we have 307 unlabeled X-ray diffraction patterns, so no label data. This is a system, the Bismuth copper vanadium dioxide system, that had not been solved by humans because of it way beyond their capabilities. We have prior knowledge, thermodynamic rules like Sudoku rules, and we know about other crystal structures that have been identified for other systems involving the same elements, but different systems. So, and by reasoning about, the known phases and thermodynamic rules, deep reasoning networks can now infer the crystal structure from the X-ray diffractions, and in fact produces this phase map. And subsequent experiments by our material science colleagues, they discover new material for solar fuels. Our vision is to build these AI scientific robots encapsulating the scientific method from formulating hypothesis, plan, execution, and interpretation of experiments, combining this data-driven and knowledge-driven approach. Here you see SARA, that stands for Scientific Autonomous Reasoning Agent. And here what you see is we depict SARA controlling laser spike annealing of experiments and the collection of synchrotron X-ray diffraction data and interpretation of the data so that it can decide the next experiment. And here is the phase map produced by SARA. So as a final example, I show here, deep reasoning for medical imaging, for producing 3D anatomical models from CT. Here we have a normal human spine, and here we have a CT scan of a spine. And this case is actually very challenging, even for expert radiologists, because of it's a severe case of scoliosis, and the metal implants lead to scattering. So it's very difficult to interpret this scan. But by combining data, learning with reasoning, now deep reasoning can produce a 3D model, generate a 3D model of the spine. So my second message is related to the transferability of AI. So I talked about, the Amazon project, but I talked about the crystal structure phase mapping, Sudokus, etc. And what you see here is a subway where the different projects, we refer to these as subway lines, the different projects correspond to stations, and the lines correspond to computational themes. And I talked about pattern demixing using deep reasoning, and in particular, how we use deep reasoning to demix Sudokus or crystal structure phase mapping or 3D modeling of medical imaging. And this is really the power of computer science, reductions, and AI, how we can transfer, methodologies across domains and actually learn and make them very powerful. That's, for example, ChatGPT can understand different language, including programming language, because of this transferability. And my final message is that, computational sustainability and AI for humanity is a two-way street. On one hand, we can inject computational AI and computational methods, inject computational thinking in terms of scientific discovery and addressing sustainability questions by providing insights, methodologies, and solutions. But on the other hand, by studying these problems, we are exposed to very exciting and new challenges. They lead to new formalism and concepts, and therefore they lead to advancement of AI for humanity. Thank you.
Thank you. I wonder, is Doug back? Doug? Yeah.
Yes, Bart. You have a question?
Yes, so I can start as a question. Yeah, so you talked about the trade. So you talk about multi-objective optimization, and I know you've done this for the Amazon project. How do the users or policymakers now choose between the objectives, or do you show the alternatives? How is if there's a trade-off between objectives, how do you present the results?
Wow, that's a very good question and very challenging in the sense that indeed our perspective has been, and for this concrete example of the Amazon, number one, show that, you can have solutions that produce, huge energy output, but can have very negative effects in terms of the other criteria. Or, you definitely want to eliminate solutions that are inferior with respect to all the criteria. So basically, we talk about these Pareto trade-offs. And in the end, we try to provide visualizations of the trade-offs. It becomes challenging, actually, when we have very high dimensions. And for example, we are seeing here we have like about 10 criteria or 10 objectives, like energy, biodiversity, deforestation, etc., etc. So we also are working on and because we have very fast methods, and just for you to see, as you increase the number of objectives, this problem is truly exponential. So we can end up, and for the Amazon, we actually can end up for the entire space with about 13 million solutions. So what we are doing is we are actually developing methods to compress the Pareto frontier and provide, typical solutions for different ranges of criteria. But that in itself, Bart, you had to ask a very hard question.
But I think you have to do time, I guess.
That's classic Bart Selman. Yes, thank you. We got to move on. So, Carla, thank you very much. On to Eric. I think he's next.
Great, thank you, Doug. Can people see my slides?
We could a second ago.
There we go.
Yeah.
Okay, there we go. We're all set.
Great. Well, there's been a lot of excitement lately about recent developments in AI. I thought I'd give kind of an arc of where I think things are going and so on. I like to partition AI efforts into three pillars of effort: principles and mechanisms of intelligence. I think we have a second pillar, human AI collaboration when it comes to real world systems, and also application opportunities and challenges, and aiming at the kind of title of this event today in terms of thinking through AI and humanity. So first on principles and mechanisms, we're at an inflection point in AI based on neural modeling, deep nets over the, basically we're only about, I'd say, 12 years into this right now, but it's amazing where we've come so quickly, given some of us on the line here who've been on, in AI for 30 to 40 years, the speed we've seen, for example, human parity reached on benchmarks in vision and language, speech, and language and vision joint challenges. And then over the last 3 years, we see what I would call an inflection on top of an inflection, the rise of generative AI, models that are trained in a self-supervised manner and that generate rich content. Many of these models are trained on a very simple objective function, and they're pushed to get better and better. And what we believe is happening is we're building rich representations of the world in these systems. Just a little bit more about generative AI. One of the earliest huge successes was the GitHub Copilot, which continues to generate guesses of the next portions of programming code that a software engineer needs. This system now plays a significant role in the daily life of millions of software engineers. In one study out of Harvard, increasing productivity by over 50%. Many folks' first exposure to generative AI came via image synthesis. And when DALL-E 2 came into the fore from OpenAI, I was working on a landscaping project, putting a pool in, which I've since abandoned. But I was curious why we had to have solar water heaters and separately solar cells to power, the house. And so I asked DALL-E, what about solar cells affixed to solar heat collectors for heating a pool? And I was really impressed by the powers of compositionality. The system could generate, kind of an idea that hadn't been created before, combining water heating with solar power generating, even showing it kind of like how the system would age, how it would look, what some of the constraints are that was being solved. Now, the headline over the last few months has been with the qualitative and quantitative capabilities we're seeing with generative models at scale. Here's the center where GPT-4 was birthed, just a bit west of Des Moines, Iowa, that provides 10,000 top-line GPUs and about 300,000 CPUs. And for the geeks out there, 400 gigabits per second of network connectivity for each GPU server. Moving ahead with this investment was in part based on understanding scaling laws. So this is what you see here is going up from left to right, 10,000 times in computation. And we have laws, empirical laws that are quite good at predicting as a function of parameters and compute and data, what we can expect in terms of the reduction in loss function or how much better we can get at predicting the next word. And you can see we landed just right on the prediction for GPT-4. We can predict these kinds of things pretty well these days. We know what we're paying for. But we can't predict emergent properties. We're seeing emergent capabilities in these systems. And these have been an interesting exploration, a topic of exploration in terms of new tasks like work by Sam Bauman, Wei, and others to show that we see kind of abruptness of behaviors arising when transitioning to a more resource-intensive model. Now, moving on to some surprising capabilities of GPT-4, my team gained access to earlier versions of GPT-4 in August of last year as part of doing earlier studies of safety and reliability. But we were really impressed by the powers we saw. The two words that came to mind for me, and we covered some of this in a paper we did covering some of the powers that we saw. The two words were phase transition from the last version, GPT 3.5, and polymathic, this idea of combining topics and methods from across multiple disciplines. We saw both general capabilities, abstraction, generalization, and compositionality that you can read about in that paper, as well as access to specialized skills like visualization and medicine, which I'll come back to in a few minutes. Now, before I go on to applications, let me talk about human-AI collaboration, just to give you a sense for where that's going, because it's a really important topic, combining human intellect and machine intelligence. People talk about augmenting humans in various ways. Well, this is a very important and challenging topic. It's both theoretical and empirical, as well as a design-oriented work. But the work that I've been very excited about is using AI, typically machine learning itself, to guide the complementarity of human and machine intellect to really figure out what the borders are, how to build systems that can really make use of the complementarity. In some of the systems you can read about online, I won't have time today, we've built systems with rich extended machine learning objective functions that understand human competency and human challenge when it comes to tasks. And that could sort of bring the machine and human together in ideal ways when it comes to like a pathology task. Another area of focus is basically on how we interleave human and machine problem solving. It's not all, there's a design issue as to who goes when and how do you actually do the conversation, whether it be a problem solving discussion or an actual language-based discussion. And over the years, we see different applications of principles we've developed and others have developed. For example, in the upper left-hand corner, you see a robotic system developed at Johns Hopkins, working at Children's Hospital in Washington, D.C., where the robot and human surgeon were working together hand in hand, coordinating on a complicated suture repair called an anastomosis repair. At the bottom is a view of work we published last year of egocentric video, someone wearing a HoloLens device. But it turns out there's an interaction between the intelligent system watching over in this kitchen situation, providing advice and labeling in a back and forth conversation. And the idea of control initiative is critically important, as it is for conversation and fast-paced discussions in this teaming event you see on the right side here. We've recently applied mixed initiative to controlling GitHub. So, we found that it's not always useful to have recommendations coming up per the original design of the system. We can use machine learning to figure out and predict when a recommendation will be accepted or rejected to a cost-benefit analysis, looking at the timing of what it takes to write your own code versus modify code and check it. And we can build systems that more ideally interleave the intelligent recommendation engine for developers with human intellect. Now, moving to applications and human flourishing, humanity, AI humanity, I'm very excited about applications in medicine, where things are going, in the sciences and in education. But of course, there are many other areas to be thinking about, and these include emerging markets, accessibility, notions of sustainability, and other areas. Let's talk about medicine as a really interesting hot topic. It's been AI in medicine, I've said for many, many years, is a sleeping giant for healthcare. There's been work over decades, our team and others, on building predictive models from data and thinking through deeply this idea of a data to predictions decisions pipeline in healthcare. We've done work, for example, in predicting which patient will become infected with C. difficile, a common infection in hospitals, within 48 hours, for example, or which patient after discharge will be readmitted within 30 days using supervised machine learning, the older machine learning, traditional machine learning. And we've built systems that, we've barely scratched the surface at getting these systems into translating them into actual practice right now. Other really challenging areas and opportunities include, how do we help physicians do better with, for example, avoidable errors in healthcare? Turns out that medical error is the third common cause of death in the United States after heart disease and cancer, per Johns Hopkins study, and other studies have verified these kinds of numbers. Can AI provide a safety net like the one that helped catch people who may have fallen while working on the Golden Gate Bridge back in the 1920s? So one example here is this really challenging phrase, which is called failure to rescue, which is a missed opportunity to save patients who die after encountering a treatable complication. And we've built systems that can actually predict from large amounts of data about people who've died in hospitals unexpectedly, to predict within 48 hours and 24 hours which patients will actually need a life-saving maneuver. Now, deep learning is seeping into healthcare applications. It's not clear how the translation has gone so far, but for example, in dermatology, an academic paper showed systems that could actually recognize patterns at the level of experts. Same for radiology, in recognizing and diagnosing conditions from flat films, for example. But what's kind of exciting now is thinking about where things are going with these large-scale language models. They're exhibiting specialist mastery. Back in last year, we found that GPT-4 could really excel at the USMLE, step 1, step 2, step 3. These are exams taken by medical students, and the step 3 is to certify doctors for practice. We also discovered you could give these systems a full case, challenging cases from the New England Journal that are considered like hard challenges in healthcare. Have the systems really go through and come up with reasonable expert diagnoses, including plans, test plans, and so on. And now we're seeing multimodal reasoning. This is the LavaMed project from our team at Microsoft Research, where you could basically take some tens of millions of images scraped off of the web, sort of medical literature with their captions, and fine-tuning a model that can now reason about imagery and text at the same time and answer questions like this. So over time, we're going to have to evaluate the power of these systems. I just gave a talk at Stanford Medical Department of Medicine at Grand Rounds, and I showed 9 cases that were just absolutely fabulous, and the 10th case would have killed the patient. So we have some work to do. But as this paper in JAMA showed, on looking at how well these generative models do with complex diagnostic challenges, they found that in 40% of the cases, the system was matching the expert diagnosis and having a diagnosis somewhere on the list of diseases in 65% of the cases. So what they called out, this was a promising adjunct to human cognition and diagnosis. It probably takes some design and that human AI collaboration to field these kinds of systems with today. If you search on AI anthology on the web, you'll find a set of essays that I pulled together as editor, one of which is on healthcare. Bob Wachter wrote a beautiful essay on where he thinks GPT-4 and models like that could help and where they're going for healthcare over time. Now let's also turn to the sciences now. I think it's a really exciting space. What we're seeing in the sciences is, the prospect, as Carla was talking about, advancing material science. There are challenge problems now, like the Open Catalyst Challenge at NeurIPS. People are using neural models to compute Schrodinger functions, for example, and other kinds of analyses that are giving us insights into how to design better materials. In biology, we have some very exciting developments. For example, going from sequences like text to 2D images, now into larger graphs that can really capture protein-protein interactions and help us reason about, for example, processes inside cells, drug targets, drug side effects, and so on. And of course, there's been a lot of excitement about these new computational microscopes we have for using AI methods to understand protein structure and function. I've been particularly excited about insights about function. Sort of the work by Humphreys et al. A couple of years ago, sort of identifying for the first time interactions among proteins that were not known before, mapping them to known functions post hoc, as well as identifying unknown functions. And now we're seeing methods that can be used to design proteins, even like using in-painting and diffusion modeling, really pioneered in image generation for protein work. Sorry about these, if you're getting these on the screen here. Over in the summer, we were honored to have a paper featured on the cover of CACM with colleagues Tom Hope, Doug Downey, Orrin Etzioni, and Dan Weld on the prospects of these systems we're developing now in AI, helping humans with scientific discovery. We wrote this paper before we could play with GPT-4. It was a little bit older. It takes a while to get papers through the CACM pipeline. But let me show you some things that we predicted we could be doing that we now can do, some of which are sort of addressed by GPT-4. One type of capability that really surprised me is that the prospect to have these large-scale language models interpret a whole paper and help us interact with it. So back in December, a paper had just come out in Nature on surprising methane in the atmosphere that increased in levels during the pandemic, sort of surprisingly, and a model from a team that described why this was happening. It put the whole paper as a prompt and asked these questions. What are the key weaknesses of the study? If we assume the author's hypothesis is incorrect, what else is going on? Did the authors overlook important relevant modeling methodologies? What are some new directions, and so on. And the system beautifully answered these questions. And the fact that it could do this and describe the work at different levels for different readership, it was pretty impressive. Now, another development that I think is really interesting is this idea of multi-step engagement and analysis that can provide a scientific advisory tool. And this is something available through OpenAI. It was called Code Interpreter, now called Advanced Data Analysis. But the idea basically of loading in a big data set, like I just was doing a demonstration, I loaded in a big climate temperature data set for worldwide. And I asked if I could sort of want to understand this data better about global warming. And the system sort of shows me the steps that it goes through. I want to see the changes in average temperatures over the summers in the Northern Hemisphere. I want to see the redder areas representing higher temperatures. System breaks the projects down into step by step. It gives me a map. Then I can sort of ask questions about the situation here and have a dialogue about what was found in that data set. These multi-step processes can be used in so many interesting ways, and we've done work, I've done explorations with physicist colleagues on large-scale data sets on particle physics, looking for anomalies. So I see we're getting to some of the processes and powers we talked about in the paper we published over the summer, written about a year before. Now, let me end my talking about science with just an interesting case here that I did in collaboration with physicist and Nobel laureate Saul Perlmutter and some of his physicist colleagues. There's a new form of matter, relatively newly discovered, called quasi-crystals. It was proposed by mathematicians a while back and then discovered and appearing in meteorites. And it's only been thought to these aperiodic crystals to occur in extraterrestrial processes. We asked GPT-4 to help us think through how this might be created on the Earth. And amazingly, we asked, the system said, have you thought about lightning strikes on bauxite mines? And by the way, you might want to look in Jamaica, because that's where we have lots of bauxite mines and lightning strikes. And this was considered a surprise and interesting and a real direction forward by the physicists who study this area, who are experts in this area. So the idea of systems like this that can bounce us out of our grooves into new ways of thinking and jog our minds is really interesting. So I'm not going to, given that I'm over time right now, I'm not going to go dive into education, but let me just say that, there's a long-term dream of building tutoring systems, and they've been very complicated to build and test. And I do think now that we have the opportunity to use these models. We've done some experiments with colleagues on reasoning systems that understand things like pace and precision and depth and metacognition. And so I'm very excited about directions there as well. So let me just summarize by saying excited about education, medicine, and the sciences. We can spend some more time thinking about the rough edges of AI, where it's going in terms of the costs and risks, but I'm very, very optimistic about these methods being, really helping humanity to flourish in new ways moving forward. Thanks.
Eric, wonderful, wonderful. And everybody out there, we'll find ways to bring your questions and other comments to Eric and the other speakers. Steve Rogers, here he is.
Okay, can you see that okay, Doug?
Looks good.
Great, great. When Doug first asked me to start thinking about, AI for humanity in 2050, it occurred to me that's, 27 years from now, and this is 2023. And so the first thing that occurred to me was, heck, I've been doing AI for 50 years this year. That's a long time. And I got to admit, don't anybody tell my wife, the second thing that occurred to me, that also means I've been married for 50 years. And I did think of them in that order. Sorry about that. But the point is that by 2050, my favorite person in the world, this little girl, Belle, she'll be 30. And so I started thinking about, what is it I want AI to provide the world when she's 30? And she's probably got a daughter of her own and is close to her daughter as Belle is to her mother, my second favorite person in the world, Sarah. And there they are sitting together at a recent soccer game where she coaches. And not unlike Eric, as I thought through where AI is going to impact humanity, my mind immediately went to addressing those things that I think we have to focus on. I mean, absolutely, as Carla and Eric pointed out, there'll be dramatic impacts in science. And as Eric pointed out, and then Tom will point out in a little while, the impacts on education. But where my mind went was the biggest thing we need to have AI address is inequities, the inequities that exist in society and exactly how it can do that. Now I'm going to focus on healthcare. Now I'm all in with what Eric said in terms of what we can do now, where we see things going. But specifically, I want to focus on how AI can address the inequities in healthcare. So fast forward, and in the early 80s, when I was a young professor, I was looking how I could apply AI to healthcare challenges, and I was exposed to the Heckler report. If you've never seen this, it's still a standard sort of report. It documents, where the world is at. I mean, if you're a Black infant in the U.S. is over twice as likely to die, about a little over 10 per 1,000 die. Versus white infants, it's around 4, a little more than 4 per 1,000. If you're an American Indian or Alaskan Native, you're about twice as likely to die, on the order of 7 per 1,000. Pregnancy-related mortality is, again, over twice as high for a minority versus non-minority. And you say, well, what's going on here? And what can AI do about that? So, I mean, as Eric pointed out, AI can bring a lot to improve the standard of care, but specifically, I want to focus AI on addressing the inequalities in care. And I think the way forward to do that is we have to get away from this sort of average outcome-based medicine to personalized care. Now, in 2000, I was actually I had left the military and I was in the AI applications of healthcare environment. And that was about the time, the first drafts of the genome were released, and we all assumed, hey, we're headed right smack into personalized medicine, but it's still an aspiration. So as I look forward to 2050, which was Rockstar Doug's challenge to me, look forward to 2050, I envision AI creating digital twins for every human. And so no longer will I, live based upon the average thing I should do to you, a person who has these conditions. I will have a digital twin to sort of, as Eric pointed out, play that forward, as Yann pointed out, play that forward and look at the impact of what I'm going to do with respect to treatment. And then via wearables, actually close that loop. I think the age of clinical trials will be completely gone because of these digital twins. We're already seeing great progress. I mean, if you've ever looked at the suicide numbers, it's disproportionate in the minority community. We're already seeing great progress in using AI to predict things like, suicide is a real risk for this person. Now, I want to hit one more thing here when I talk about healthcare, and that is, you can talk about the technology, but my experience with a decade in the healthcare commercial world taught me a valuable lesson. It is not the technology. You can have the best technology. My team and I actually had the best computer vision algorithms for the early detection of breast cancer. That is not why we became commercially successful. So when I entered into that business, which I didn't understand business at the time, my partners were drug dealers from Canada. Well, they were in the pharmaceutical business. I'll be a little clearer than that. But they wanted to get into the diagnostic business. And so they funded us to, create this product, to develop the science and technology for the early detection of breast cancer and to field it. While we did that, it became obvious to us we could apply that same AI to predict compound and molecule characteristics, which they could use in their drug applications. And we came up with a molecule that had better potency, better metabolism characteristics than the one that they were making all their money on. And after about 8 months after we had shown this to them, I had dinner with one of the founders, and I asked him, why haven't I seen any progress in you taking that new compound to market? AI had pointed us to a far better compound than they were currently using, and he explained to me the business of pharmaceuticals. He had $1 billion compound, $1 billion a year compound. They weren't going to touch that market. And one of the lessons that taught me was as my AI guys were developing better and better computer vision algorithms, my board of directors, after we went public, wouldn't let us release them. It became, when does it make business sense? So back to my AI inequities in healthcare, I'm suggesting to you the way AI will do this is it will make personalized medicine a good business decision. No longer will you have to focus your product on the average large population. It'll be focused on the individual. And so it will make business sense. I'm one who attributes this inequality not to systemic racism, but to just the system, the way the system is built, the way the incentives are there. And I think the same thing applies to, violence. There is undisputed fact that violence is disproportionately impacting minority communities, and similarly with income. And I'm just going to throw out a rather controversial statement. Most people suggest AI is going to lead to massive unemployment. I think the exact opposite is true. I think AI provides us a path forward to full, meaningful employment. I mean, we're seeing great progress in taking people who aren't educated in computer science, able to use AI to do really interesting things, which they can monetize. So I think full meaningful employment is where we're going. I mean, if you look at the generative AI that Eric was talking about, we can have kids, building things, out of the box. Now we're doing a lot, reaching out to minority communities to do things we care about using AI. We just recently, the Department of the Air Force opened up at Howard, a university affiliated research center. That is great. And I'm all in to, change the economics, get more minorities into AI. But that's too late. There's clear data that shows that the neurocognitive deficit in these inner city kids, by the time they get to adolescence, they just have already taken that brain damage where, we've just put them at a disadvantage. I think we've got to address the inequities in this world. Now, I know I've sort of hit this from the perspective of the upside. And as Eric points out, we can spend a lot of time talking about the threat that AI presents. But I got to tell you that a lot of that, quote, threat is associated with people's fear of AI doing something that isn't aligned to their values, to their core beliefs. Now, I've got some really bad news for you. We don't understand human cognition. I got exposed to the challenges we have in understanding why we make decisions we make back in my 70s and 80s when we were looking at knowledge engineering. And it wasn't that the people we were interviewing were trying to mislead us. We really don't understand why we make the decisions we do. We have access to consciousness, but consciousness isn't even present when we make most of these decisions. We can't align to ourselves, much less how are we going to align an AI to a cognitive us, which we can't access at the conscious level. What I think is going to happen by 2050 is we're going to have a much better understanding to human cognition. That will be the key to AI addressing these challenges we're looking at. Now, at the bottom of this slide, I'm going to shamelessly plug, there's a group of us, and everybody's welcome to join us every Friday at noon Eastern Time. We get together, the group is called Quest, to discuss what is consciousness, how does it impact your cognitive ability, and if you will, what's its cash value, and what is its implications for AI. I cordially invite anybody and everybody to join us for those discussions, because my 2 cents, the answer to Yann's challenge is the reason that it works, that is generative AI works so well in text, is because it's already chunked into these primitives of the representation, which we call words. Okay, I contend all of your conscious experience is in terms of these primitives, which we call qualia. And so I think we can answer Yann's representation challenge by understanding the primitives of conscious experience, if you will, qualia. So I'm going to stop there, hit escape, and hopefully stop sharing.
Wonderful. Cap, thank you. That was excellent. All right, ready for our next wonderful thinker, my dear friend, Kimberly. And take it away.
Right, so I think before we delve into it, Doug, I think it's important to understand first what AI is and what it isn't. And first off, we tend to talk a lot about AI like it's a single technology, something that you buy off the shelf. And AI is not a single technology. It's a collection of approaches that brings intelligent behavior to software systems. And so the specific tools and techniques that's at the forefront of AI will continue to change. We're going to see the boundary of AI capability moving. That's going to shift the specific technologies and skills that's needed. But the general ability to recognize progress while we're continuously assessing limitations and potential failure modes will continue to be very important, especially as improvements to performance may make it even harder to see some of the limitations. Now, when we talk about transformational impact of AI, and we've seen quite a bit of transformation, some may argue that it's not transformation in AI models itself. The improvements might be due to transformation in the hardware, okay? But needless to say, most of the transformative impact of AI really comes from the bottom, like for many other organizations, especially in the business sector, where we're starting to see promises for new job opportunities in the field of AI, as well as other related fields, such as data management and analysis, as well as prompt engineering. We're certainly starting to see increase in competition and innovation. I think companies are starting to leverage a lot of these AI models to improve their competitiveness. There's certainly potential to significantly increase productivity gains across numerous different sectors, okay? But as we move closer to the top, looking at the mission support, warfighter capability, the components that are very unique to the DoD that nobody else is going to solve for us, okay? We have to work very closely with industry and academia to address much of the challenges for the joint force. And in fact, I'd say to tackle a lot of the DoD specific challenges, we have to move from point solutions for individual problems, the centralized AI approach, to a more integrated AI-centric approach, which is certainly going to require development of distributed hierarchical AI frameworks. That's going to be very important to support multi-level orchestration of AI and autonomy components, and do that at scale. Now, of course, when we're talking about DoD-specific applications, we have to take into consideration complexities of the real-world environment. We have to not just think about the machine side, we have to think about the human factors component too, because at every step, we have a human, the warfighter, who interfaces with those systems. So the human system balance of roles and responsibilities, and understanding what roles goes to human versus machine, when the human is either in the loop or on the loop, are things that we have to consider. And we have to think about ways in which we could use natural language processing, or even make use of the breakthroughs that we've seen in large language models for context parsing in order to detect and mitigate deception tactics to ensure survivability of a lot of the AI enabled systems when employed. Now, when we talk about deception, I want to spend some time unveiling some of the hidden risks there, because again, the adversary always has a vote. Deception tactics has been used throughout the history of warfare, as you know. Much of autonomous warfare, I would say, like any other warfare, is going to be based on deception. And it's going to create a very dynamic threat environment. We've already started to see AI fooling humans. There's even a reality series that's now on Netflix that's called Deepfake Love, to supposedly test the strengths of relationships using deepfake technologies. We've seen image-to-image translation, text-to-image translation, face aging, text-to-video. We've seen improvements to generative text models with multiple optimization, inference, and decoding techniques that are used to inject finer levels of control, which means as we develop a lot of these technologies, we have to be very, very thoughtful about how we design solutions for a particular use case. And we've already seen AI fooling AI, whether it's via digital or physical input manipulation, and poisoning data attacks or their backdoor attacks to alter training data. Simple patches even to a stop sign can evade detection. So AI systems are very brittle. That's the truth. And so to use AI responsibly, we have to understand the vulnerabilities and fragilities. And simultaneously, as we develop a lot of these AI tools, develop a lot of intelligent autonomous systems, we need to think of ways to protect our systems, ensure our systems are robust against adversarial manipulation and deception, robust across a range of functions, robust across different environments. Take the right steps to minimize the risk of model inversion, and hence decision manipulation. Because at least for the DoD, I mean, you scan through a lot of the policy and strategy documents, the one recurring theme is looking at ways in which we, the department, can utilize AI in order to gain a decision advantage. Okay. Now, when you look at the threat surfaces along the training and inference pipeline, and really start to add in threat surfaces, you see again the clear threat surface here is in the training data on the left, with the potential to even bypass filtering and processing using approaches such as decomposition attacks. Okay, so to use AI responsibly, there has to be transparency, first off, in dialogue among academia, industry, and government. And we have to be clear about what we want to be robust in order to make AI models very secure. Now, considering that there's always a human component to this, like I said, whether the human is in the loop or the human is on the loop, we need to also have a very consistent way to measure and evaluate user trust in, or even trustworthiness of a lot of these AI systems in context, and do that over time. In fact, when you've seen probably the responsible AI tenets that we've published across the department, one of them is warfighter trust. And so to address the warfighter trust component, we've stood up a Center for Calibrated Trust Measurement and Evaluation, CATE, to really help operationalize responsible AI. And much of the emphasis there is on warfighter in the loop, design, and evaluation. So looking at ways to advance some of the foundational science and practice of test evaluation, V&V, of a lot of the AI and autonomy component, and to include establishing courses for continuous test and evaluation V&V of these AI systems, starting to outline the engineering landscape, thinking about common standards and frameworks, methods and tools, how we provide a coordination point for end-to-end engineering, for how to develop, build, test, evaluate, maintain, and even modernize trustworthy military autonomous systems. We are starting to put together a test bed with, again, for human in the loop experimentation, so we can measure and evaluate user trust in and trustworthiness of a lot of these systems in context over time. And since a lot of the AI or ML components are often the least trustworthy parts of any AI-enabled or autonomous system, we're looking at ways in which we can tie formal concepts within machine learning to engineering properties, okay, taking a systems engineering approach and exploring metrics and procedures to test models for much of those properties. And of course, again, we have values and we have the ethical principles to think about. So really, we've emphasized the ethics and security by design, making sure when we design these systems, they can operate in accordance with our American values and our ethical principles as we've outlined them. So lots of activities across the AI space, whether it's in the business sector or it's within the department. But when we talk about the future of AI, I mean, yes, we're going to see breakthroughs in hardware. And like I said, I think a lot of the breakthroughs that we're seeing in AI is because we have the compute power to date. I think we're going to start getting to the point where we can even run hybridized AI algorithms, neuro-symbolic algorithms in an analog digital space and within a symbolic or even data-driven information space to provide the robustness or even predictable classification of the electromagnetic environment, and to do that in a very energy efficient manner. We've already started to see the power of human AI synergy. There are a lot of tools that are in development, co-pilot tools, where the human is really an integral part of the system. Like I said, we're certainly going to move from centralized AI to distributed AI systems, systems that can learn in a federated manner. However, when we talk about the most transformative breakthroughs, I think, again, it's going to likely come not just from AI alone. It's going to come from the convergence of neuromorphic networks, which are really bio-inspired, and quantum technologies, again, thinking about co-development and co-design of software and hardware. Okay, it can't just be a software alone conversation. And we know quantum technologies, if you think back to quantum mechanics, certainly brings a lot of value to the table. There's quantum parallelism. So we're going to have very fast processing, or at least there's the potential for that, of large amounts of data, unparalleled energy efficiency because of single quantum processing approaches, cybersecurity. I mean, quantum systems by design are very secured systems. And then there's how we learn. How do we integrate quantum sensing, perception, and processing for operation of quantum AI systems? But as I say that, though, I'm also mindful that we need to understand the implications of all of that on trusted AI. Now, workforce is an important consideration in the conversation because, again, we have to educate that future workforce. We have to understand the limitations. We have to understand the risks. There are benefits, but there are risks involved in implementing a lot of these AI tools. And there's so much still that we don't understand. So when we think about the future workforce, I'll tell you, it has to be a multidisciplinary workforce. They have to have a very multidisciplinary background. It's not just, you know, data scientists or machine learning engineers. It's really thinking about that fusion across advanced mathematics, some of the statistical methods combined with systems engineering. Okay, we've taken a lot of steps to build where we are and develop principles for software engineering. And we're certainly going to start building upon those software engineering principles as we push towards AI engineering. But our workforce needs to catch up with the pace of the thinking and the developments as well. We've got to put programs in place that educate them. They've got to understand the AI system security threats. Robust AI needs to be a part of the conversation, what it means when we're talking about scaling AI systems. What are the security risks there involved? Can we trust the outputs, okay, at scale? There's the human-centric component, because again, like I said, the human gets a vote. We cannot divorce the human factors from the advancements in machine development. Quantum AI needs to be a part of the vocabulary, just like we've been talking about more of the neuromorphic systems. Responsible AI and thinking through the requirements and validation, foundational practices for continuous test and evaluation, uncertainty quantification and calibration, all parts, needs to be all part of the conversation. So we're going to see AI driving workforce needs at multiple levels. There are certainly core technical roles where we're going to have, for example, algorithm development, data engineering, the AI test and evaluation, the leadership roles as well. Leaders really do need to keep aware of capabilities and limitations of the technology, but at the same time, be very open to new approaches, but also be able to resist the hype. There's a lot of hype. We'll certainly be using AI-enabled tools across these different roles. But again, the specific skills needed to work with AI-enabled systems effectively is going to keep changing, and it's going to look very different for different jobs. So while today we're starting to think about that certified AI user, I think as we continue to evolve in this field, there won't be a common certified AI user type of training. I think the one skill that may be broad enough to hold up in the face of such a rapidly changing technology is a mindset to be open to experimentation, but skeptical, and to think in the sense like test engineers do. If I'm planning to use this AI tool in my workflow, what might go wrong? Okay, how does it cause trouble for me? Can I come up with some hard cases to see how this tool might backfire? Where does it break? And only then do we really understand how to use a lot of these tools responsibly. So when we talk about AI for humanity, Doug, I'd say it's really humanity choices or values and how we collaborate with AI that's really going to shape the future. And again, it's the intersection of AI with other technologies that's going to be the most transformative.
Wonderful. Really good. The next speaker is Tom Mitchell from CMU. And Tom is also known as Tom Terrific. He's really made a difference to a lot of us and what happens with machine learning.
Thanks, Doug. And thanks everybody for being here. What a great session. I'm going to keep this short enough that we will really have time for a discussion at the end. So I won't tell you about all the things that I think are interesting about AI, but I will tell you what drives my own interest. For many years, really, it's two threads that drive my own work in AI over the decades. One is trying to understand learning in humans. We've done studies in humans and in machines. And my guiding principle is, and I think it's still true today, is if you want to know the future of machine learning, all you really have to do is look at how humans learn and machines don't yet. And I'll give you an example. We're all familiar with systems like ChatGPT, large language models that have amazing capabilities like we've been hearing about from multiple speakers. And if it weren't for machine learning, we wouldn't have those systems because, as you probably know, they're trained on huge amounts of text taken from the web. But what you might not have noticed unless you kind of thought it through is those systems, they don't learn anymore. Once they're trained, we use them, we have conversations with them, but unless somebody decides to retrain the whole thing, they don't continuously learn. If you look at people, people learn every day, every week, every year, every decade. We learn many different things in a kind of synergistic way. And so much of my own research in the last decade or so has really been around how can we build never-ending machine learning systems? How can we build AI systems that, as a byproduct of being used, just become better at what they do? So that's part of what drives me. The other thing that drives me is I genuinely believe that AI is going to make a huge impact, positive, and some unanticipated, probably negative, on our lives over the coming decade. And the one area that I want to talk about today is AI in education. And I'm convinced that if AI is ever going to make a difference in how we teach people, then this is going to have to be the decade for that. And here's my reasoning. Number one, we've known for many years that if we can have a human one-on-one tutor a student, that student learns 1 to 2 sigma better than the normal distribution of students. Put another way, that student who's tutored, if you compare them against a student who's not individually tutored, but sitting in a generic class, the tutored student on average will outperform 90% of the students who are not. So we've known that for a long time. Of course, we can't afford a human tutor per human student, but we can afford a human computer for every student, a cell phone or a laptop, whatever. So the big opportunity here is to build AI-based educational platforms that really can customize to individuals. And the final part of my argument is, for the first time in history, we finally have multiple online education platforms out there that have taught millions and millions of students. And so those platforms have training data about how to teach, what works and better, what works less well, that they've gathered for millions of students. And that gives them more teaching experience from which they could learn to teach better than any human teacher like myself would get if we taught for 100 years. So let me share the screen here for a minute or two and show you. Here's an example of what I mean by this. This is the front page of a website from a nonprofit company in California called CK12. They have, over the last 15 years, had over 230 million distinct students use their website, answering over 1 billion questions and putting in 40 million hours of learning. Just to put that in perspective, 40 million hours, I did the arithmetic, is 45 centuries. That's a lot of data. So what does that data look like? The data looks like this. This is data from Squirrel AI, a different online company. This is log data of one student going through one lesson for 1 hour and 49 minutes. First, the student took some pre-test questions. Then they watched some videos. They solved some practice questions. They studied the solution. They started watching another video, but they dropped out, did some more practice. They took a post-test. They reviewed their performance. We get keystroke level log data in these systems for millions of students doing this kind of activity. So now the brain teaser is, how can we use this data to learn to teach better? And honestly, my real goal here is to use this teaching platform, CK12 in particular, teaching platform, as a platform for research on how to build never-ending learning systems. I want to use this as our next attempt to build a system that literally the more it teaches, the better it learns to teach. So how can we go about that? The way to think about it is to first ask, what are the specific types of knowledge we need in order to teach well? And how can a teaching system like this acquire that knowledge? And I'll talk about 3 types. The first is, if you want to teach a student well and personalize to them, you have to become good at diagnosing their knowledge state. Here's a student coming through the math course. I want to know at each point in time which concepts the student does and doesn't understand. If it's a 3rd grader doing arithmetic, maybe they understand multiplication, but not the carry part, or division, but not remainders or something. We want to know that. And to turn this into a machine learning task, the way we handle this in our own work, and many others do the same, is we set it up as the problem of predicting for each question that's available in the system. Often there will be thousands of questions that the student could be asked. We want to learn what's the probability that if we ask the student question I right now, what's the probability they'll answer correctly? And so we can set this up as a standard large data, big data machine learning problem, because remember, we have data from millions of students where we see the history of what they've done so far. We see them answer a question incorrectly or correctly. And so now we can learn how those symptoms that we've seen in their history, which features of that history predict whether they'll be correct or incorrect. What's the state of the art on this? Here you can see the state of the art. Here are 4 different data sets from 4 different education platforms. If we try to predict for every question whether a student answers correctly or incorrectly, if we basically guess, we'll be correct 50% of the time. If we predict based on not this student, but what's the average correctness or incorrectness across all the other students, we can do better than 50%. But if we train a model that using machine learning that's looking at the history of the student, we can do significantly better. Still not perfect, but I'm a human teacher and I can't predict perfectly whether a student will answer a question correctly or not either. Okay, so point 1, we can already in these systems use the data from millions of students to get a leg up on predicting for future students which questions are going to be able to answer correctly and incorrectly before we ask the question based on what they've done. What's the second machine learning task? We want to then use this to learn to choose the best teaching action. For example, here's a question from biology. Integral monotopic proteins are permanently attached to the membrane from what? Okay, here are 4 possible answers. We took on the problem of if a student answers a question incorrectly, which hint should we give them before they try a second time? And we have for each question, usually on the order of half a dozen human-authored hints. Here are the ones for this question. And you can look at these yourself and try to figure out which hint would be the best one if you want to maximize learning outcomes for the student. Well, it turns out, again, we've got a lot of data. We collected data for 142 days on over 1,000 such questions, collecting 3 million plus student hint experiences. And we found that, in fact, hint 1 is the winner here by a significant margin, although paragraph is not bad either. But these have dramatically different effects, not only on the second attempt correctness when the student tries the question again, but also on the final learning level that they achieve at the end of the lesson. Okay, so point 2, not only can we learn to capture the student's knowledge state, we can use that to help predict which hint to give to the student. The final thing I want to suggest is we can also now, because of systems like GPT and others, take on a new problem of generating new content. When I had the system learn which hint to provide, what it was really doing was choosing among existing human-authored hints. But what about using GPT to author its own new hints? So I'll just give you one example. I gave GPT-4 this question. Suppose Mary drives from point A to B at 100 kilometers per hour. Bill drives from B to A at 50 kilometers per hour, both leaving at the same time. Will the paths cross, and if so, where? Well, interestingly, it answers this question correctly. But more interestingly, I then said, suppose the student answers incorrectly, that they will meet halfway between points A and B. What hint should we give the student to help them without giving away the exact answer? And it came up with this. It says you could say something like this. Remember, they're not driving the same speed, so they won't meet halfway. Think about who is driving faster and how that affects where they will meet. The faster driver will cover more distance in the same amount of time. That's a great hint. And so the idea here is we haven't injected this yet in the system the way we have the first two learning capabilities that I added. But now we're hoping to be able to add this to the system so that we'll have a kind of synergistic collection of learning tasks all going on simultaneously, learning how to better and better estimate the knowledge state of each individual student. Number two, learning how to choose which teaching action, which hint, for example, to give to a student, given their history. And number three, generating new content like new hints. And I'll just end by showing you a little bit of entertainment. At the end of this, I was thinking about motivation of students and customizing the hint and the problem to the interests of the individual student. And I have a granddaughter who's a fan of Taylor Swift. And so I said, well, give this hint, this advice in the style of Taylor Swift. And here you can see it rewrote the hint as a song by Taylor Swift, where the chorus is, you got to focus on the distance they travel before they meet and their paths unravel. Mary speed is faster, that's a fact. So halfway between A and B is not where they'll act. Okay, I'll stop there. Thank you. And Doug, we can open it up for questions.
We got to get Clive Davis to check those lyrics.
You're right. Well, the thing is, it could customize to different styles. I had it rewrite the hint in the style of Muhammad Ali also. I can share that with you later.
Okay, well,
I wanted Tom to sing it. I wanted Tom to sing that Taylor Swift rendition there.
Yeah, Tom, I'll catch you later because you and I have a few things to think about. And now you added some icing on the cake about Ali.
Deal.
Okay, well, let me turn to a couple people other than just the speakers. You know, Mark, are you there?
I am, Doug. First of all, great set of presentations. Really inspires both hope and deep fear.
Okay, we don't have a bio for Mark or Bart, but these are wonderful colleagues I've known for decades and decades, and he's a heavyweight.
So I did actually just get weighed, and I did actually gain 5 pounds. So I'm feeling a bit sensitive there, Doug. But I promise to exercise more. My question actually is, wonderful session on the future of humanity that's dependent on AI, discovering new knowledge we heard about, educating our children, robotic surgery. We're creating pharmaceuticals for our health, generating information for our democracy. We didn't hear a lot about that, but that's obviously a very important topic. Even transporting our loved ones. And I guess, and I know several of the speakers have worked in this, and I think it's an important question, particularly given the president's just released guidance on responsible AI. I mean, how can we trust society's well-being, indeed humanity's future, to a technology that's today vulnerable to data poisoning, model bias, privacy and IP loss? How do we ensure AI becomes a force for good?
That's a loaded question.
Are you asking the other panelists or the
the other panelists? Yeah.
Oh, my sense is that we can't be assured, and that we're entering a really interesting disruptive period. I think we're all hoping that for good disruptions, good surprises, but we have to be prepared for inadvertent influence as well as malevolent uses. And back to your question, probably the more expected answer is we iteratively work on regulations, including laws and penalties. We monitor. At Microsoft, you probably saw, I think you saw popping up on my screen, red teaming going on. We have quite a bit of an effort internally on self-regulation right now that we would imagine would inform the kind of red teaming, and it has been an input that the government and other governments are asking for right now. So there will be standards of practice where we actually do put our systems through a battery of tests for resilience, robustness, and you know, given that we can't, for example, when it comes to errors in a medical system or inadvertent lyrics in an education system trying to give hints, we can at least be transparent about statistics, and we could have, like, we call transparency notes that come along with these tools, so people who know how to use them and understand their limitations, like any product safety kind of approach.
So warnings and labels, Eric. You know,
as one piece, we have also regulations and laws, standards of practice, UL approval, external audits that are third-party audits. You can imagine rich sets of approaches to keep things in place. I mean, you wonder about how it was back in, I don't think there was the same kind of hue and cry, but in 1897 was, what do we say about electric power? This might be game changing. We need to regulate it. We need outlets that are all the same in the United States and world. Maybe we'll let Britain have their own outlets, their own configuration. We won't push on that so hard, but standard electric grounding rules. And so, I think that it's interesting in many ways. AI will probably interleave and innervate society more deeply than electricity. Is my sense, given what it'll touch as these technologies edge into this for the first time into the realm of the kinds of tasks we've relied on human cognition before, which is a pretty big deal.
If I can add one point to this, so we could also, in addition to electricity, make the analogy to what did we do when computer viruses came out? Remember the Morris worm that was like 1980?
That's right.
And up until then, like computer viruses were not really a thing. And then all of a sudden they were a big thing. And one of the more effective things that the country did was actually stand up an organization called CERT, Computer Emergency Response Team, which had two functions. One was to detect and advertise the existence of computer viruses, just to post them so that people would know and how to deal with each one. And second, what their second role was to collect and disseminate best practices. So no matter how much we try to anticipate what AI will do, we will be surprised, as is suggesting. And so I think there's a lesson there too, which is we want some kind of robust, rapid, light on its feet detection and monitoring and dissemination.
A number of our products that we ship through the Red Team at Microsoft, it's called the Deployment Safety Board, the DSB, feared by everybody because it holds up products, and some are sent back to the drawing board. But one thing we do ask for at times, I'm on that board, is monitoring and response, like monitoring and fast response. I was going to say, Tom, back to your example, I still remember when David Heckerman and I, we were looking over we had never seen a spam, the ARPANET was like, we'd never seen like an advertisement come in email. We were so intrigued. We said, wow, look, an advertisement on the internet. Wow. It was for legal services, believe it or not. And we were so amazed by this. But now we have spam filters, so, and it's like, no, everybody knows what junk email is now. It was like this. We were so excited about it. We printed it out. We bought it home, said, hey, the internet's getting commercial.
The amazing thing is that the internet has existed for a decade while you were a grad student. Before that ever happened, before there were the spam, that it made it for a decade without spam.
That's great. Can I jump in on you two Stanford grads? Grant, are you looking into the ability to turn on a mic for somebody in the audience?
Yep, I just need to know the name of the person who would
Okay,
like.
I'll let you know shortly.
Okay.
So Bart, one more question for you, please. You are my bringers in the audience.
Yeah, just maybe a question for Tom. I found the whole well, what is the impact on medicine, healthcare? It's clear from the talks that the impacts of AI are going to be incredible. I enjoyed seeing Eric's overview of how rapidly the field is moving in the last few years. It is incredible. But Tom, you talked about how we can improve education, and I see all the opportunities. What's your thinking of what we should be teaching our students? Because I actually feel there may also be a significant impact of what topics and how we teach our students. For example, coding, to what extent, how do you teach it now when there's a code assistance? I do see that there could be quite a significant change in sort of in what we actually teach or how we teach it, or what students should learn. Have you thought about that?
Yeah, great question. It's the flip side of how we teach is what we teach. Many people have, one slogan that I've heard now multiple times is, you will probably not be replaced by an AI system. You will probably be replaced by a person who knows how to use an AI system. And so I think part of the answer to your question is, just like when calculators came out, and the good engineers all learned how to use calculators, they became good engineers that way. I think it's going to be the same in many walks of life. That's kind of a lesson for continuing education. If you ask about primary education, I think it's harder to answer that, but one way to look at it is to think these systems like GPT are going to do for each of us individuals what today only CEOs get. So CEOs can afford a team of specialist advisors to collect the information for them when they have a decision to make. I don't get that because I'm not a rich CEO, but today I go to Bard and I go to ChatGPT and I go to these systems and I get kind of that. And so we should be teaching, maybe the lesson there is we should be teaching in primary education, people to be decision makers, CEO-like decision makers, by using these tools as advisors. One thing.
Yeah, very good.
Okay, great. I have a friend who I'm going to call up to a microphone. I know they're working on turning on his microphone as we speak. His name is Rush Holt, a very well-known name for those who know physics, or later on, some 17 years in Congress as a member of the Federal Congress in Washington, or after that, as CEO of AAAS. And now he lives in an office next to Einstein's office. Anyway, do we have the microphone unmuted? Hey, Grant, I'm going to talk to you through the system.
Yes.
So,
he's allowed to unmute now. I've asked him to unmute and he has permission to talk.
okay, and he has the ability to turn on the camera if he wants?
He should be able to.
Okay, I have, let's see, I have unmuted, I think.
I can hear you. Sounds great.
Hi, yeah, I'm Rush Holt. I know several of you and admire your work over the years, and it's good to hear really a very stimulating discussion. Doug, thanks for setting it up. And I wanted to ask, well, this is kind of related to something that came from Bart and Mark and Kimberly. I was looking at the the statement from the White House on the new executive order and the fact sheet and comments that go with it. And I was struck by a couple of things. It's very generic and non-specific, and it could apply to almost any instrument, not just AI, any new technology. But what's different about this, it starts with a very negative presumption, I think. And I'm wondering whether other people notice this. In the executive order, it's talking about safety and security and trustworthiness. In fact, they use those words. But the implication is this has enormous risk of being unsafe, insecure, and untrustworthy. And therefore, we need to put in place watchdogs, enforcement of transparency, fairness panels, and that sort of thing. And I'm wondering, should we, should we accept what I think is a presumption here that there's an asymmetry when it comes to AI, an asymmetry between the benefits and the risk, the benefits and the risks, the harm and the opportunities. If not, if there is a symmetry between, well, if there is an asymmetry, I had to figure out, well, what is it about this? How is this different from other tools that need regulation? Is there an asymmetry that should be described better? Or if there's not, should we do something to counter this presumption of asymmetry that is, there are 30 bills before Congress right now. Not much has been legislated so far about AI, but there are a lot of people who are itching to do it. And in order to get that to work, I think we'd better figure out what kind of a threat is it? Is it different in scale just because this is a more powerful technology? Or is it different in kind from regulations that are necessary for communications and transportation and kind of any number of other things that the government speaks about and regulates on? Does that make sense to any of you?
It does to me, Rush. Nice seeing you, hearing you. I'm a big fan of the first pass when it comes to AI applications and their influence on people in society to seek responsibility in today's regulatory agencies versus thinking we need something new and different. NHTSA, NTSB, FTC, FDA, these people are expert and for years been working on regulations. They have to ask the question, what's new now about the housing folks, for example? What's new now about this technology that they might need to modernize some of the things they're doing or add new kinds of regulations? I don't think there's one way to say that there is a single asymmetry. I think the cost and benefits and the risks and value will vary not only by the domain and application, but by the case. And we can sort of sum over those cases and get a sense for different areas. One concern that comes up among people on the fairness topic is, yes, we've had unfair practices based in unfortunate aspects of our society and the data associated with it that trains our AI systems for decades. What's wrong with the AI systems doing the same thing that people have done for decades? Well, this idea of automating in a homogeneous way, in a uniform way, and in a very implicit way, biases and dark matter in decision making, where we're putting some people at less opportunity than others in a mechanized way is kind of a scary prospect. So the fact that we now have codification representations where we can actually explore and understand better some of the biases in our systems that may come from our own society for the data that they're trained on is an opportunity in some ways to fix things, make things better, and to avoid this idea of the algorithmic amplification of these biases.
You know, but Bart, I would just.
Hey, wait, real quick. I want to say thank you to all the speakers, and that includes Rush, Bart, and Mark, yourself. But in any second, we might get cut off. Go ahead, Mark.
No, I was just going to agree with Eric. I don't think it's necessarily an asymmetric characteristic. Rather, as we were describing before, it's a technology that has, like any new technology, limitations. I like to just amplify something Eric said. I use the words biased, brittle, and baroque. Namely, it's the old reference to dull, dirty, and dangerous. And why? We're worried about things like bias, like Eric was just talking about, brittleness, where things don't apply. There's a number of comments in the Q&A, or it's opaque. It's baroque. It's not clear what the heck's going on. I think many of those things are soluble, like Eric was talking about with red teaming and there are other methods, bias detectors and so on. I think a lot of these actually are technological limitations, weaknesses, just because of the state of the art. So I think we're going to overcome those. I think the government has a responsibility to protect its citizens, if not even the world. That's why we had a declarative policy many years ago in DoD that we would not use AI in human targeting. That would be a human process. So there's an example of where society has decided, even before the White House was thinking about regulation, to self-regulate. And we've seen this, of course, in biology and other areas as well. So I do think the scientific community, we have a responsibility to describe the dangers and the risks, to identify them. But to your point, I do think perhaps the perception might be overly negative. I actually think the good is going to outwin the evil here in the long term, and that the benefits, and this is a much more, as Eric and others have said before, this is a much more powerful technology because it applies to everything. It can change everything. And therefore, I think we have a responsibility to make sure that it's developed in a way that's responsible. And so I think the good news is everybody's aware of that now and are working toward that, both from a regulatory perspective as well as from a scientific perspective and implementation. So I'm very actually positive about the future, but I think we should be generally positive.
I think a friend of ours has a wonderful quote. AI is the new electricity. It's everywhere. Again, I want to thank everybody for being involved, talking about what you're thinking. You're wonderful colleagues, and I hope everybody had fun. That was the optimal word for the day. Thank you.
Thank you.
Thank you, Doug.
Thank you. Wonderful meeting, Doug.
Thank you.
All right.
Beautiful.
I'll catch you all later.
Bye-bye.